In this video, we introduce Newton's law of universal gravitation. We explain how gravitational force depends on mass and distance, show that the force acts along the line joining the center of mass, and connect universal gravitation to the familiar expression for weight W equals mg. Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force that depends on two things: the mass of the objects and the distance between them. The equation is F equals g times capital M times lowercase m divided by r squared. Here, F is the gravitational force between the two objects. Capital M and lower m represent the two masses. The symbol r is the distance between the center of the two masses. And g is the universal gravitational constant. The value of g is 6.674 times 10 to the power negative 11 newtons meters squared per kilogram squared. This is a very small number, and that is why the gravitational force between everyday objects is usually extremely small. The equation tells us two important relationships. First, gravitational force is directly proportional to the product of the masses. If either mass increases, the gravitational force increases. Second, gravitational force is inversely proportional to the square of the distance. If the distance gets larger, the force gets smaller very quickly. For example, if the distance between two objects doubles, the gravitational force becomes 1/4 as large. If the distance triples, the force becomes 1/9 as large. That square on r is very important. Also notice that r is measured from center to center, not surface to surface. For spherical objects like planets, we treat the mass as though it were concentrated at the center when applying this law outside the object. Now let us look more carefully at the direction of the gravitational force. Gravitational attraction acts along the line joining the centers of mass of the two bodies. On this diagram, one object is labeled lowercase m and the other is labeled uppercase m. The force on each object points toward the other object. The smaller mass is pulled toward the larger mass, and the larger mass is also pulled toward the smaller mass. This is where Newton's third law becomes important. The magnitude of the gravitational force is the same on both objects, but the directions are opposite. So if Earth pulls on an object, the object also pulls on Earth with the same magnitude of force. That may sound strange at first, because Earth does not noticeably move toward the object. The reason is that Earth has an enormous mass, so the same force produces an extremely small acceleration for Earth. Remember Newton's second law. Acceleration equals force divided by mass. Same force, much larger mass, much smaller acceleration. This is why the object seems to fall toward Earth, while Earth's motion is too small for us to notice. The important point is this: gravitational force come in equal and opposite pairs. But equal force does not mean equal acceleration. Acceleration depends on mass. Next, let us calculate the gravitational force between two ordinary masses. In this example, we are asked to find the magnitude of the gravitational force acting on each particle. The two masses are m1 equals 12 kilograms and m2 equals 25 kilograms. The distance between the two particles is 1.2 meters. The question asks for the magnitude of the force. Magnitude means we only need the size of the force and not a positive or negative sign. The diagram shows the direction separately, and the force on M1 points toward M2 and the force on M2 points toward M1. Because this is gravitational attraction, the forces point toward each other. They are equal in magnitude and opposite in direction, consistent with Newton's third law. We use Newton's law of universal gravitation to solve this problem. The equation for the Newton's law of universal gravitation is F is equals to G times M1 M2 divided by R square, and we can substitute the numbers. So G is 6.67 times 10 to the power minus 11 newtons meter square per kilograms square, and multiplied by 12 kilograms times 25 kilograms divided by 1.2 meters square, and this gives us 1.4 times 10 to the power minus 8, and we can see this units m square cancels out with this m square, and then kg square here at the bottom cancels out with these two, leaving us with newtons, and we get units of a force. So the answer is 1.4 times 10 to the power minus 8 newtons. This is extremely small. That makes sense because the two masses are not very large and the gravitational constant G is tiny. The force exists, but it is far too small for us to feel in everyday life. The force on M1 has the same magnitude as the force on M2. The directions are opposite. M1 is pulled toward M2 and M2 is pulled toward M1. So the final answer is not that one object pulls harder than the other. The forces are equal in magnitude, opposite in direction, and acts on different objects. Now let us connect this universal law to the familiar idea of weight near Earth's surface. Weight is the gravitational force exerted on an object. Near Earth's surface, we can use Newton's law of universal gravitation to calculate the weight. If an object of mass m is near Earth, the gravitational force between Earth and the object is given by W is equals to the universal gravitational constant times the mass of the Earth times the mass of the object divided by r squared, and here r is the distance from Earth's center to the object. At Earth's surface, r is approximately Earth's radius, so we can use r sub e for that. So here we use capital R, and we can rewrite this equation. So W equals G m e m divided by r e squared. And here we can factor out the object's mass and the remaining quantity. This part can be written as lowercase g equals g m e over r e squared. Now if we substitute the values, mass of the Earth, the value for the universal gravitational constant, and the radius of the Earth, and calculate this value, we can find this g is equals to 9.8 meters per second square. So that is the value we know as the gravitational acceleration. This shows that W equals mg is not a separate law. It is the near Earth version of universal gravitation. This also helps explain the difference between mass and weight. Mass is a measure of how much matter an object has, and it does not depend on location. Weight is a force due to gravity, so it can change if g changes. For example, your mass would be the same on the moon, but your weight would be smaller because the moon's gravitational field is weaker.